We're about to start the afternoon session. My name is Jeff Wall. I'd like to first introduce our Senior Vice President of Knowledge at Google, Alan Eustace. And I don't know, Alan, it was about 8 years ago or 7 years ago, we kind of started all this stuff together. And but following Alan, we'll do our research lightning talks.
So, well, thanks for inviting me. I'll also do a lightning talk here, mostly because Maggie just asked me to do this like 2 seconds ago. So I've got a long prepared set of remarks here. Mostly, I just wanted to thank you. I mean, from Larry and his staff and myself. I mean, research has always been really important to the company. We started the company basically coming out of Stanford. I just had my 10-year anniversary here. We've always had a really strong and I think healthy relationship with the research community. We've tried really hard to find good jobs for your students. We've tried really hard to build an environment here which people find active and creative. It was started as you walk around. I hope everything feels somewhat familiar. That the energy level and the creativity and other things really is meant to reflect universities, because I feel like that's where a lot of the most exciting and most innovative things in the world happen. And I think companies do well to emulate universities whenever they can. I'd also like to thank you, on behalf of the company. I know a lot of you had to travel a long way to come here, and there's a lot of friends and family in the audience here, people that I've interacted with for many, many, many years, way too many years, honestly. Not because I don't want to interact with you more, it's just we're all getting a little old. But anyway, it's just fantastic to see you all here. It's just, as I talk to people, I get really excited about all the new and interesting things people are doing, the way people are tackling problems, the fun problems that people are working on. It's great to see. So please take advantage of your time here. Google is just so happy to host it. And if there's anything we can obviously do, please let somebody know here. So with that, let's move to lightning talks.
Hello everyone, my name is Vivek Kwatra. I am part of the Machine Perception Research Group, and I will be talking about video stabilization on YouTube. I will be doing the presentation, but this is joint work done with Matthias Grundmann and Irfan Issa. So I don't know how many of you own mobile phones with video cameras, but I bet it's quite a few. And if you've tried ever capturing a video with your mobile device, you might have realized that it's quite difficult to keep your hand steady, especially if you're trying to look at the action and the scene as opposed to the camera itself. So let me play a video which is captured using such a handheld device. And you'll notice that the content in the video is somewhat interesting, but the camera motion itself is very distracting, and you're trying to probably stabilize this in your head, and it's sort of making your head hurt. So let me just move on and show you what you might want to see. And this is the result of stabilization using our algorithm. So what you see on the top now is the stabilized result. You can still see the content, but the motion is now much more stable, and so you don't have to actually stabilize it in your head. It's much more pleasant to watch. If you look at the bottom, that's the original unstabilized video, the shaky video. You also see this red rectangle, and this rectangle is what we call the crop window. And this is sort of what lets you do the stabilization. It's actually following the camera motion, the shake in the camera, and letting you just see the stabilized version. So what you see at the top is essentially what's within the crop window. You'll also notice that while the shake has been removed, you still see the original intent of the camera. So you do see the linear pans, you do see the zoom in and zoom out and so on. So I'll give you a brief overview of the basic ideas behind our technique. So our goal was to essentially start with casual video, something you capture on your mobile phone or what you commonly see on YouTube, and make it look more professional. So we started by looking at what do professional cinematographers do. And the key observation there is that they plan their camera moves. So for example, they'll use a tripod to compute a perfectly, or use a perfectly static shot, get a perfectly static shot, or they'll use a dolly to get a linear motion. Now we want to do the same or get the same effect, but after the fact, where the video has already been captured and is shaky to begin with. So now if you think about these camera paths, these smooth camera paths I just described, mathematically you can actually describe them using just the time derivatives of the path. So if you think of a static camera, its first derivative in time is 0. If you think of a linear motion with constant velocity, then its second derivative is 0. So the idea behind the stabilization technique is to cast this as an optimization problem where you're trying to minimize the norm of these derivatives. And we do this in this L1 norm framework. And the nice property of that L1 norm optimization is that it gives you these sparse solutions, which effectively results in paths which exactly follow one of these derivatives. So let me show you in this graph here. So if you look at the graph, the red path is the original shaky path. The blue path, the thin blue path, is the stabilized path. And what you see in these bolded segments are sort of these key things that come out of it. Oh, by the way, this is from a real video, so this is an actual solution. So if we look at the bolded red vertical segment, that is perfectly zero motion. So the algorithm comes up with perfectly zero motion, which corresponds to like a dolly motion. If you look at the green segments, these are perfectly linear segments with constant velocity, and they correspond to a dolly-like motion. So that's sort of the basic idea. And if you want to make it work on YouTube, we have to do a few more things. Firstly, we wanted it to be fully automatic, so minimal user interaction. And what this entails is figuring out what should be the size of the crop window that I showed you in the beginning. And we can automatically compute that based on the content of the video, how much shake there is in the video. So if the video is shaky, it will be a smaller crop window, and then we dynamically adjust it if the video becomes stable. Secondly, we have graceful failures. So for example, if the video is too blurry or the camera suddenly drops, then we can take that into account by progressively making the motion models simpler. And finally, which is sort of the distinguishing feature on YouTube, is that it allows you to do a real-time preview. So you can see what the stabilization would look like approximately before you commit to it. And to achieve that, we actually divide the video into chunks. We do this camera motion computation in parallel, and then feed the output of the camera motion to the stabilizer, which then crops the video and then feeds at real time to the user. So let me show you a demo of that. This is a recorded demo. So let's say if you have a video, and this is the watch page. If this is your video, you'll actually see a button on the top which says Edit Video over here. And once you click that, you enter this UI where you see the original on the left and the enhanced on the right. Once you click Stabilize, there's a small latency of a few seconds where we start computing the camera motion, and then we start streaming the stabilized result to you on the right. So what you see on the left is the original shaky video, which is from a head-mounted camera of a person running. And what you see on the right is the stabilized video where most of the shake due to the running is taken out. And if you like it, then you can go ahead and click Save. And this is being streamed in real time, of course. Something we launched recently is also rolling shutter compensation. This is an extension to the stabilizer, which can handle rolling shutter cameras. So most of your mobile cameras have what is called electronic rolling shutter, which means instead of capturing the entire image at once, it captures it one scan line at a time. And what this means is that there is a small delay between the various pixels in different scan lines, which effectively results in non-rigid distortions. And so to take those into account it's a somewhat orthogonal problem to the shake problem. And so what we've come up with is what we call the calibration-free approach. And the idea here is we don't want to know what device you captured your video with, because on YouTube we don't really know, or we don't always know what the device was. And so sort of that's the nice thing about this calibration-free approach. I won't go into the details. Instead, I'll play another video. So this is an example from CitizenTube where regular users upload videos of news events. This is from the Virginia beach crash, and the user here is probably either running or on a bike, and there's up and down motion, but there's also significant non-rigid distortion if you look carefully on the left. And what you see on the right is the stabilized video where all those non-rigid distortions have been taken out. Let me just go forward a little bit, where you might see more distortions. So this motion on the left is fairly non-rigid if you look carefully. And on the right, you sort of take those out by our method. And here are a few pointers. So you can go to YouTube. You can go to the editor, which is a full-fledged editor. You can use the enhancements. That's the demo I showed you. We also have suggested edits where the content is automatically analyzed, and then once you upload a video, it'll suggest you to stabilize it if you want to. And then this is a fairly popular feature. We've already had usage in the millions of videos which are being stabilized. We have a couple of papers. One was in CVPR last year, and then one was recently in the Computational Photography Conference on the rolling shutter removal. So if you're interested, you can go refer to those videos, get more details. Thank you.
My name is Ed Chi. I am a staff research scientist here at Google, and I joined about a year and a half ago. I have two quick little topics I wanted to talk to you about. The first one is privacy and sharing in social media. And one of the interesting things about social media is that we all are still in this giant experiment. And in fact, the biggest experiment probably has to do with the circle model in Google+. So when I joined, I became very interested in understanding this problem, which is, I'll summarize by the following way. That if you think of some of these existing social medias that have been there before G+ came along, basically what I have been saying is that let's make broadcasting information as public as possible. And the reason for that is because we want it to go viral, right? We want information to be as free as possible, right? But the problem with that is that it doesn't mirror the real life. In real life, right now, we have these doors closed. And if you're outside, it's very hard to hear what I'm talking about. There are real organizational boundaries as well as personal boundaries and social boundaries where information shouldn't cross over. And so the whole idea of circles was to try and see if we can model this real life. So which one of these two possibilities are actually the future of social media? In physical life, when we share, there is this physical space that governs how we share. I just had a conversation with Jeff Hare about this, right? But when you go online, what happens is that all your friends belong to one circle. And anything you share, including the conversation that you had last night while you were puking over the sidewalk because you had too much to drink, all goes on to Facebook or Twitter, and everyone is there to see it. Things like, for example, maybe not something you should tweet. And things like, for example, this, read the second tweet. It says, oh, by the way, I want your hot body tonight, baby. And this happens to be a celebrity somewhere in a different part of the world, not in the United States. But this was a big scandal. So Dana Boyd has talked about these problems as context collapse, right? And other people have talked about in terms of these sort of real life social network. Paul Adams has a series of famous slides about this. And what's really interesting about this from a social media perspective is that there is a privacy paradox. And what does that mean? The paradox is that if everyone really truly cared about their privacy, why is it that so many people are using Facebook and so many people are using Twitter, right? Despite all these stories about how these things seem to fail, people continue to use these systems. So we went and studied the actual real data in G+, and then published a paper about it. And what we found actually was, I think, actually quite surprising. 75% of the users actually used circles as a way to manage their audience. And in fact, nearly about a little bit over 2/3 of the items shared in G+, at least in the first month or so, were shared to circles, not shared as publicly as possible. So they were providing some of the first evidence that people indeed want to organize their contacts and want to manage their audience. The question is whether this will persist. Some of the latest data that I can't talk about actually does suggest that this trend is continuing inside of G+. If you actually look at the circles that people use, they say things like church, music, Google, tech, Twitter, photographers, celebrities, etc. And if you actually do some basic analysis of these circle names, what you find out is that, first of all, we seem to have missed having the default circles like work and school that are very, very important in people's lives. those were not defaults in G+, and they probably should be. But also that they start to organize their context into weak and strong ties. This is something that Eric Gilbert, who's in the audience, have written extensively about. And what's interesting is that it seems to actually confirm to some rather nice social theories that actually was taught by, I was taught by Scott Clemmer, who's also in the audience, of these ideas of personal spaces. That the fact that, for example, I'm from Taiwan, where personal conversation distance is about 1.5 meters, whereas if you're from Spain, it's probably more like half of that, right? And these are things that social psychologists have actually studied. So the point that I'm trying to get at is that this is the giant experiment that we're having, and we're starting to collect data, and we're starting to understand these user behaviors. People indeed form these inner groups, these structure groups, interest groups, and these sort of miscellaneous weak tie groups that they're using in their contact management to deal with their real life sharing problems. And the experiment seems to be paying off. Users are indeed using circles to manage their context and their audience. And so if there's one thing that I hope you're taking away from this couple of minutes, is that there's this, from an HCI perspective, the real need to really think about what I call the holy trinity of social media, which is context, audience, and context. All right, so how did I do on time? Okay, all right, so divider star. It's me again. So next thing I wanted to talk to you about is the perception of social annotations. And again, this is a paper we published in 2012. If you think about the fact that we have this amazing search engine, and where does it need to go to in the future, you realize that it needs to become more personalized, and it needs to take into social information. The future of search requires really deep understanding of these users' context, in particular the social factors. And the reason for that is because these social factors are the things that we truly trust, right? I mean, when we look at information, the reason we trust Wikipedia, or maybe you don't, or whether you trust information from REI or from any other sources, reviews from Amazon, for example, is that you have some computation about the social context in which these information occurs in, and you have some inherent trust around them. How can we actually get search engines to understand this context so that we can actually show the appropriate information to the user? About 1.5 years ago, we launched a product called Social Search that actually shows these social annotations. You can see that there's a search result with a URL, and then there's a snippet, and then underneath it, there's this little, what I call social annotation, which is a picture with a name attached to it. And the presumption is that you'll see these social annotations and you'll make decisions about whether to trust the search result, and this help you decide whether you're going to click through or not. So the question is, how do these social annotations actually affect user trust and behavior? What we did was we actually went and did an eye tracking study using what we call retrospective think aloud interview. What that means is that we actually have them be brought into a lab, do their organic search as much as organically as possible, as naturally as possible. While they're just, if they want to talk, they can talk, but if they don't want to talk, they don't have to. And then we show the eye tracking traces actually back to them. And then we ask them, what were you thinking about when you were looking at this search result? You glanced over and you didn't pay attention to the social annotation. Why is that? Right? And so what we did was we had these 18 to 20 tasks. People came in for an hour. Half of them were social, half of them were not social. So they couldn't exactly tell what we were up to. And we had tasks spanning a set of different task domains, how-tos, products, navigation, etc. And we developed, like good scientists, we developed hypotheses about how people are going to react. I mean, we thought, okay, if it's family members, then they really care about those social annotations. If maybe it has something to do with contact expertise. So for example, if I knew that Bill was really into wine and there's an annotation about wine, then I'm going to trust Bill, right? And maybe it has something to do with search intent. If I'm there to actually buy something or choosing a restaurant, then I'm okay, but otherwise I'm not. So the big surprise actually turns out to be that subjects didn't even notice the annotations. So of all the chances to actually notice the annotation, only 11% of them actually had any eye trace actually rested on the social annotation. Okay. So study 2. Why don't people see these social annotations? What we did was we did a bunch of design variations. So for example, we put the snippet at the bottom, put them at the top, we make the pictures bigger. We varied snippet length from 4 lines to 2 lines to 1 line. And we changed the position. This is a manipulation check. They should pay attention to the result in the first position better than they pay attention to the result in the second one, right? So to summarize, what we found was actually annotation placement makes a big difference. If you put it above the snippet rather than below the snippet, it makes a huge difference in terms of how many people actually notice those annotations. And more interestingly was actually the snippet length affected how much people pay attention to the annotation. The thing that you need to pay attention here is that the dark green line here is the numbers. It's the number of fixations on the snippet. This is 4 lines, 2 lines, and 1 line. And then the black bars here are the number of fixation on the annotation itself. You see that the more people pay attention to the snippet, they pay less attention to the annotation text. So the one nice summary, without going into all the details of the eye tracking and all that sort of stuff, is that subjects first always pay attention to URLs and titles, and then they make a decision about whether to click through or not click through. If they decide to click through, they don't need to look at the snippet. If they decide not to click through, they don't need to look at the snippet. It is only the case when they couldn't decide about whether to click through or not that they started reading the snippet. And since the annotation text, it's part of the snippet, they do it in reading order. And that's why placing it at the top is better than placing it at the bottom. And the longer it is, if you put it at the bottom, then it takes longer time for them to get to it, right? So it's by doing eye tracking that we actually found out how they actually do it. That's it. Thank you very much.
Good afternoon. My name is John Wilkes. Many of the people that are talking to you today are going to be describing things they've already done and presenting some spectacular results. I'm not going to do that. Many of the people who are going to be talking to you today are part of Google Research, and it's a fabulous organization. I am not part of Google Research. Many of the people who are going to be talking to you today have spectacular graphics and fun images and things like that. I am not going to do that either. Word of advice for anybody who wants to give a talk: don't ever share the stage with children, animals, or people from the HCI domain. So what I'm going to talk about is the stuff behind the scenes. If you can see what I do, I have done something horribly, horribly wrong. Cluster management is our name for, think of it as the operating system for the fleet of machines. We have a very large fleet of machines whose precise size will remain slightly vague at the moment. Those machines live in clusters which are subdivided into cells. Cell is an organizational unit. Think a median-sized cell is something like 12,000 machines. Each cell has a manager associated with it. On each of those machines, a little agent which will do things at the manager's command. So the thing that makes Google particularly interesting, and the reason I'm having so much fun here, is that everything here is very, very big. Much bigger than anything that you can imagine having played with anywhere else, at least in my prior life. Before I joined Google, I was working on a petabyte scale storage system, which we thought was at the extreme edge of what we thought we might be able to accomplish. When I got to Google, I came across this wonderful quote from Luis Barroso: "We panic if we only have a few petabytes of free space in a single cell. It's about to run out." That changes things. The main thing it changes is that stuff breaks because we have so much of it. If you're relying on 10,000 machines to do anything, you cannot rely on all of them to be up at any one moment. They never are. We did some work on a petabyte sort, trying to see how long it would take to do that. There was no run of that petabyte sort during which a machine did not fail. not one. So the question that happens now when people are doing design discussions is not how can we make that go fast? That's easy. We just throw more machines at it. The question is what happens when that breaks and that breaks, and then you don't have a person awake to deal with the issue. So we get to learn how to cope with things failing all the time. And that actually is much more interesting than trying to make things just go fast. Make things go fast, yeah, fine. It's easy to get 5% performance improvement. Making something work all the time, much harder, much more interesting. Okay. So as you might notice, Google has made available a bunch of interesting things to you. Not surprisingly, that runs on our cluster machines. So we do actually have a cluster operating system, a cluster management system. The old one is now about 7 or 8 years old. It's getting a little long in the tooth. In Google terms, that's probably 3 generations for most of the other pieces of software that we write. We're still running on that first generation thing. As you can imagine, it has, as I like to say, evolved organically. Everything you can think of about software engineering implications of that are true. So we're building a second system, and I use the term in the special meaning that Fred Brooks meant it. It has all the properties you might expect of that second system, but I'm going to focus on the 2 positive ones that make it interesting. I'll leave you to speculate about the rest. So from our users' point of view, we're trying to make, our users are the internal folk in Google, and the other guys who are going to be talking today and tomorrow. Our goal is to make their life more predictable and easier. Our goal is to make sure they spend less than 5% of their time dealing with things like the stuff we offer them. It should just work. They shouldn't have to say how it should work. It should just work. We'll come back later what that might mean, might be interesting. Internally, our goal is to try and make the thing so we can respond faster to yet more inane requests. More important requests that come from our internal customers about things they need to be able to do. And just a little bit of fine print, this system is called Omega. It's not in production. It might not ever get into production, though I think it will. Everything I say should be taken with a small grain of salt. This is what it looks like. I don't actually want to spend any time discussing the design of the system other than to say it's really cool and be happy to talk about it afterwards. What I would like to do instead is to poke around some of the things that are causing us to stay up at night. What can't we do? So I'm not actually going to tell you anything we have accomplished. I'm going to give you some examples of things I'm not quite sure how best to accomplish. We will find ways to do them, but we'd like to work with people like yourselves and your students to find better ways to do them. So here's the first one. In the middle of this system is the thing that the user is trying to run. It doesn't actually matter what it is. This happens to be just a random application. All of those little boxes around it represent a software system that those users have to understand, deal with, interface to, work out how to configure, and coax into doing what they want. Is this good? What should we do about it? Clearly, this isn't a smart way to make progress. If you look at something like Google Docs, things like the spreadsheets and the documents that we can edit online, to launch one of those things needs, the authors of Google Docs have to interact with about 50 internal systems inside Google. 50. Getting a version of Google Docs up and running in a cell is a magnificent accomplishment. And then the guys who manage the resources come along and say, could you move that to another cell tomorrow? That is much harder. We don't actually know what the dependencies are on the local versions of things. For example, suppose there's a configuration file. Is it important that configuration file comes from the local copy of Bigtable, or just is any copy okay? So it turns out that simple automated detection of dependencies doesn't work because those little exceptions kill you. Manual provision of information about dependencies doesn't work. No, you know what engineers do? They're lazy. Why would I specify something if I don't have to? And our current systems do not make them do that. So guess what? So problem number 1, if you can make configuration easier at scale in the face of continuous failures, that would be wonderful. Be happy to talk more about those issues. To make it easier, wouldn't it be nice if we could say, here is my program, run it. I don't want to say anything else. It should just work. We can actually get quite close to that with App Engine. I don't know if you guys have used that, but I'm actually a customer of it. And you just launch it, and it sort of mostly works. And it sort of has a default performance behavior, and it sort of has a scalability thing that pretty much does what you want. If you look a little closer and you want a little more dependability, you might want a few more knobs. What happens if I suddenly get a workload spike that increases my load by a factor of 10? Should we handle that, or should we say no? What happens if the workload changes? We used to do really simple things to do, and now they get complicated. What happens if Michael Jackson dies again? A lot of these things you can measure. Performance you can measure, right? The latency looks like it's a little worse than we'd like. Let's throw more resources at it. Okay, great. Which resources? Does it need more memory? Does it need more machines? Does it need more CPU? Does it need more who knows what, right? So that just finding that out itself is hard. We could do experimentation. There's a bunch of incredibly smart machine learning people around who could help us with these things, and that's one of the paths we're thinking about going down. But availability is a little more awkward. Let's throw something away and see how many people complain. It's probably not the best recipe for finding out whether it's the right thing to do. But if you're looking for concrete examples of things to help with configuration, automating the process of setting some of the millions of knobs that systems guys like me are happy to put in because we don't understand what you want, automating that would be really cool. Because you won't tell us what you want. I've tried this. Go up to somebody and say, tell me what you need from running this application. They don't have a clue. They'll be delighted if it doesn't fall over. Okay, drilling down a little bit on the inside of our system, we care a lot about availability, as you probably guessed. So wouldn't it be nice if we could have the system decide where to place things to minimize the chance of a concurrent failure of multiple things at once? It's easy enough to handle sort of onesies and a single machine's breaking. But let me give you a concrete example. We have, most of our data centers pretty much have a tree-like power distribution topology. There's, the utility provides a bunch of stuff. It goes through these massive things called PMDCs, which have generators sitting next to them. Those go to bus ducts, which are wasping great pieces of copper about like this, and those go down to sort of the circuit breakers and stuff like that. And you could easily see that one of those branches could break, and what you want to make sure is that you don't have all of the instances of your stuff on one of those branches. Great. Smear stuff everywhere. Well, life isn't quite as simple as that, of course, because there isn't just a single topology. There isn't just a single tree. We think we know roughly how to handle a single tree. If any of you have good ideas about how we handle multiple DAGs simultaneously overlapping one of these things in order to get replacement, come talk to me. We actually are trying to work out how to do that right now. Okay, so we talked a little bit about this in terms of how do you ask customers what they want. Well, the standard way of expressing this is a service level objective. I would like it to go this fast. I would like it to be this cheap. I would like it to be, etc. Great. Which things should we offer people? What do they actually care about? How do we know? How much do they care about them? What happens if I could make it go twice as fast, but it would cost 3 times as much? Is that a good trade-off? The answer is, it depends. So how do we get people to express those trade-offs in good ways? So that's what I call the SLA question. How do you write a good SLA? Most of the SLAs that you and I experience in real life are not really things we can change, right? The cell phone company gives us an offer and we say yes or no. We don't get to negotiate with the cell phone company. I'll double the price of how much I pay if you increase the quality of my phone calls. I wish I could. So how do you find those things out? I mean, one model is the standard poke in the eye with a big stick. If that doesn't work, okay, let's try a smaller stick until you stop complaining. But underneath a lot of the things that I'm trying to describe is how do we get people to understand what is happening? The previous one, it was how do we get to understand what people want? The mirror image of that question is, I've got a really complicated, hairy system that nobody can understand, even the guys who are deploying it. What happens when it does that? What should I do about it? Why didn't it do X? Why did it do Y? Why did it do X and then Y and not Z? And what can I do about it? It's okay to say, the system was busy. Great. What should I do next? It's okay to say, that machine failed. Great. What should I have done to avoid the effect of that machine failing? So explanations that make sense is the slogan that I'd like you to take away from this part. How do we make systems explain to their users and the people who manage it what's going on? So talking of people who manage it, this is a thing that happens. We don't like it to happen, and we pay the people to whom this happens extra in order for them to compensate for it, and they drink a lot of scotch, it seems. We wake up our SREs, our operator types. Think of them as operators with PhDs. These are really smart people. We wake them up with a slightly hungover state at 3 o'clock in the morning with a pager. They have 15 minutes to come back with some kind of coherent response. By that stage, they probably have not fully digested the coffee. And they're faced with something that all of the automated systems we've managed to muster cannot handle. We're already at the point where we don't really understand inside the system what's going on. What they want to know is, are we actually in trouble, or is it one of those pesky idiots that's woken me up at 3 in the morning because they don't understand what they should have said? Or are we about to get into trouble so I can actually finish my coffee and deal with it in the next 20 minutes? I don't have to panic now. But again, what should I be doing? This is particularly interesting. You can imagine just during the day, right? The system is doing the following. You should do nothing. It's fine. most of the time we want to say that. The system is doing the following, you should plan tomorrow to be able to have more resources for that. The system is doing the following, you should do this now. But I don't have the authority. I, the system, don't have the authority to do that because it means turning off, I don't know, ads. That would be unpopular. Okay, that's basically it. What I would like to... The message I'm trying to get across here is that we have better problems than most other people do, which is why it's really fun to be able to talk to faculty and the students that you can send to us. So be happy to talk to you in some break, and hope you enjoy the rest of your stay. Thanks.
Okay, this thing work? It does work. So my name is Alon, and I'm a database guy. I said this in public, okay. So you're probably expecting me to talk to you about the big data that we have here at Google until you weep and offer your help. But instead of that, I'm going to do something else. I'm going to give you a different spin on big data, okay? So so I lead the IAM in Google research, okay? And I'm going to talk about stuff that we did and stuff that we don't know how to do or that we hope to do sometime in the future, okay? So we have a team of people in Google Research who work under in the group of structured data. And we have a very different problem. We have a lot of relatively small data sets, okay? And when I say a lot, basically any number you want, I can give you that number of data sets, okay? So right now, we're in hundreds of millions, but if you come tomorrow, I'll give you more. But that's only one aspect of it. The second aspect is, again, big data, is we have a lot of people who want to look at that data and do stuff with it. So the days where the only person in the organization that could deal with data was a DBA and we had to pay him or her a huge amount of money to do their job, those days, they're still here. But now we have a lot of other people who are very interested in data and want to do stuff with it, okay? And the other thing is we have entire populations. Okay, this is me getting excited on my slide, but we have a lot of people who are actually looking to see what this data means to them on a day-by-day basis. Okay, so we've got people doing stuff with data, and we've got a lot of people looking at the data. For a database guy, okay, these are very, very exciting times. Okay, so today, every organization, every government is being pressured to put all the data, their data available. Right, this is becoming the norm. So here's an example of a table that I have. This is a great table. It's an HTML sitting there on a web page. And if you look through the Google index, and this is an HTML table, right? So if you look through the Google index and you look for how many HTML tables do I have, something like 20 billion. Okay, that's a really, really big number. Okay, the problem is that over 99% of them are what I will call pure, not very good data, okay? I won't use my French here, okay? So people use HTML tables in order to format stuff that should appear in rows and columns, but it's not what I would put in a database or consider something that I would like to do database operations on, okay? But the nice thing about the number 20 billion is that even after you throw out 99%, you're still left with a lot of data, okay? So what we did was, the first thing that we did was, before I talk about what we actually did, so now you have all these data sets sitting around. The real potential is when people start putting them together in interesting ways. And these are people who are actually interested in various domains. They're not SQL people, SQL geeks like I am. Okay? So this, for example, came out using a tool that I'll tell you about in a moment, about a week after the earthquake in Japan last year, where somebody took a data set that showed all the earthquake activity in the world since 1973. So red means very much every earthquakey area, okay? And they joined it with a data set that showed where all the nuclear plants in the world. So the obvious question was, hold it, where should I, where is it likely to see, are you likely to see disasters like in Japan? So this is two data sets that were created completely independently, being put together very quickly by somebody who knows nothing about databases, but wants to create a visualization right now, because in a few days that question will not be as interesting. Okay, so the potential really is when you have hundreds of millions of data sets is what happens when you start combining them. What happens when people with different expertise, different interests, different cultural backgrounds start putting them together and telling stories about them. So the first thing we did, or actually the second thing we did, was we created a search engine. Okay, a search engine for tables. So we have Right now, we're serving something like 80 million tables because we're really limited it to the really high quality ones. And as you can imagine, search for tables is very different than search for text because all the signals in text don't really work well for tables. Okay, so there are a bunch of papers that describe how we do this, and you can go to a tool that we call Fusion Tables, where you can do a search and you can look at these. The second thing we did was we created a tool called Google Fusion Tables, which is supposed to be database services for the 99%. Okay, so you don't have to. In databases, we ask schema first or schema later. We don't even ask schema. Okay, we don't even use that word anywhere. This is stuff for people who are interested in data and don't have database expertise. So that this is a visualization created appeared in the Wall Street Journal. In fact, the creator of this visualization, Susan McGregor, is right here in the audience. She was a journalist at the Wall Street Journal, is now a professor at Columbia. And journalists are, in fact, a great audience for this tool because they are the ones who want to tell stories, they get the data, and they have many people looking at their sites. So these are people who act as a great amplifier for data sets that are sitting out there. And in fact, one of our greatest happinesses is the fact that journalists are using this tool with abandon. Okay, there's another this guy. So this is an example of where this guy Simon Rogers from The Guardian in the UK, when the WikiLeaks data came out a year and a bit ago, he took all that data. So the American government is not very good at hiding their data, but when the data does come out, it comes very beautifully geocoded. Okay, so you're getting high quality stolen data, and so he just put all this data on a map. Okay, and this map, for example, this is in the data blog, the Guardian data blog in the UK. This map got something like 100 million page views on a weekend. Okay, so you can see the effect of data really, people really finding it interesting. So Google Fusion Tables has been around now for 3 years, and it's getting better and better, obviously, every week. There are things that we did not anticipate would happen. So, for example, or uses that we never anticipated. So, for example, this is somebody recording. This is a crowdsourcing application. So now imagine the new kinds of data sets that people can create when you can have access directly from your mobile phone that goes into a Fusion table and things happen. So these are the potholes in Spain. Okay, as you can see, they created in Spain, but there are potholes elsewhere in Europe. So this is people just driving along the road and hitting a pothole, saying what they feel at that moment and pressing on their iPhone, and you get a new dot on the map. Okay, this for the local governments, this is actually a very useful data set that would otherwise be really hard to create. So what are the questions? I was told that we're supposed to ask questions. So I'm asking questions. Okay. So we're database people, which means we have limited imagination. So the question is, so we have all these, what are the other interesting things that we can do with 100, 200 million tables? Okay, I should also say in Fusion Tables, you can take a data set and make it public, in which case it gets added to the corpus of search that we give you access to. The second question is, as I told you already, there's a lot of, let's just say between you and me, a lot of crap, okay, in these structured data sets. How can we distinguish the good data, the authoritative data, from the data of lesser quality? Okay, this is a huge problem because when you start putting data together, you really need to have good data. Make sure the data actually is relevant to what you're doing. It's not just that it joins in the right way. Okay, you have to make sure that it actually is, its meaning is appropriate for what you're trying to do. How do we what is that question? How do we convey the complexity of structured data to people? So structured data gets very complicated after a while. Okay, because people are modeling very subtle aspects of certain domains. How do we expose that to users in such a way that when they start doing things with their data, they're not taking data that was not intended to be used in the way that they're using it? Okay, this is a question on our mind. And the fourth question, which I can answer very clearly, is I heard you wrote a book about coffee. Is that really true? Yes, it is true. I took an empirical approach to coffee as of a few years ago. So this was actually a way of debugging Fusion tables. Okay, so I would take all my data about coffee, put it in Fusion tables, and find some bugs. I also traveled to about 30 countries to actually taste the coffee in different places, so I can report this to other people. The book is called The Infinite Emotions of Coffee, and I see a few people in the audience who I know have this book. So that's it. If you have any questions, I'll take them now or I'm out of time.
Hi, my name is Praveen Paritosh. I work in the Google Knowledge Graph group. I joined the group by previously working at Freebase, and before that I worked building reasoning system on using the Psych knowledge base. My talk will just quickly describe what human computation is. I think Alon just mentioned crowdsourcing, which is the more popular term used. I will describe the specific context of the ways in which we use human computation for the knowledge graph. And then I want to discuss what I think is a large fertile ground of research that is relatively unexplored at this point in time. And I'll introduce like this device, this human computation spectrum, to talk about that. So Louis von Ahn wrote a thesis titled Human Computation, and that's sort of kicked off a set of really interesting work. The idea is that you outsource steps that are difficult to automate to humans, thereby accomplishing things that would be expensive or hard to do computationally. Examples are things that involve language or speech or vision, for instance, labeling images, looking at whether search results are relevant. Oh, I'm sorry. So labeling images, looking at relevance of search results, and so on. The most interesting success have been in the realm of citizen science, where there have been interesting examples where the kind of work that perhaps an early grad student would be doing in a lab can be outsourced to volunteers, and with some spectacular results. An important thing to note is these tasks are they vary quite widely in how difficult or complex and what level of education or training is required to do them at a useful level. Who are these human computers? So there is broadly, there's a group of human computers that are anonymous in the sense that somebody who's working on Mechanical Turk, whom you don't directly engage with. You have an ID, but you don't know who this person is, and you don't have long-term relationships. While on the other hand, you have identified contributors in the sense that volunteers who have given you their identity. In the case of citizen science, people participating in these crowdsourcing human computation tasks are listed as authors on resulting discoveries, as well as contractors mediated by Odesk or employees. The context of knowledge graph. Freebase is a widely available, freely available knowledge graph. It is akin to Wikipedia for machines. The scope of Freebase is encyclopedic. It contains 23 million entities and about 500 million relationships between these entities. This process of building such a knowledge graph requires reconciliation. Reconciliation is answering the question whether two different entities from different datasets are indeed referring to the same concept, same entity. This task turns out to be fairly complicated, and errors in doing this have expensive ramifications. For instance, if you can imagine a knowledge graph where you have two different entities that perhaps are named San Francisco, referring to two different cities, if you merge these two different cities, the San Francisco in Argentina with San Francisco in California, thousands of facts that were previously connected to these nodes are now incorrect. So making mistakes while with reconciliation has expensive implications. And automated methods across the encyclopedic domain do not produce the yield and precision required to build a usable knowledge graph. And this is the reason why we need human computation. So here's an example. I wouldn't go into a lot of detail about the kind of process for reconciliation. The task that you just saw, are these two things the same? The key issue is that when our contributors begin working on this task, when the human computers begin working on this task, we do not quite yet know what is the correct way to do the task. The task instructions or guidelines have not yet been written. So we have a process in which we have three big phases. One we call guidelines generation, followed by a calibration, which is a test, followed by collection, where we actually collect the majority of human judgments required. And the first step is a collaborative step where people work together to build instructions for the task. And as they run into disagreements or issues that they can't answer, they discuss it in a forum collaboratively to build this task instructions. And so the main point I want to convey with this slide is the model where you get a human computer to just provide you a judgment and you're done with the interaction is not sufficient for doing long-range tasks. The task might require on-the-task training that is a side effect of engaging in that task. So here's a controversial slide. What I want to do is there's this hypothetical scale that I'm trying to explain. On one end, we have computation. And on the other hand, we have things which we think are explicitly the province of humans. And somewhere in between is the Turing test. And in theory, the Turing test is what is dividing the space that is fully computation from the part that requires humans and cognition. And where various things on the scale have been placed probably change over time. So for instance, it's possible that at some point, chess was probably considered on the right side of the Turing test, or some aspects of language, speech, and vision might move along the scale. But this is a picture at any point in time and technology, we can order various cognitive activities along this spectrum, the human computation spectrum. Here's a few more things to illustrate what this might mean. So right around where the Turing test is, we hope that CAPTCHAs are right about there. They have to have another property that they have to be easy and cheap to generate. But they distinguish humans from computers. So in theory, they are telling us they're somewhere in that point in that scale. And the different kinds of human computation, like games with a purpose, or the kind of tasks that are being done on Mechanical Turk, or Odesk, or with private contractors and employees, fall on various points of the spectrum. And one reference that I used here is Odesk makes a tally of like how the work is allocated across different subjects, different areas. And that demonstrates that there is a lot of, more than half of work that requires really serious training or qualifications or education before you can do that. And so what I want to argue that it seems that a lot of our research in human computation is focused on that area around the Turing test and CAPTCHAs. Well, it seems like a lot of work that is being currently done is moving towards the right side of the scale, where tasks require training, complicated instructions and guidelines that have to be generated out of the task. They require process. They are not atomic tasks. You actually require collaboration or a sequence of judgments before you can get a useful resolution. Quality becomes harder to assess. Consider how we don't actually get an accuracy score in most day-to-day employment because it's really hard to assess what is good over time. And this requires thinking about issues of long-term relationships as how the contributors working on the task or the human computers are getting educated and trained. So it starts to look like the kind of stuff that we have to do to get professionally educated work. And it raises a whole bunch of problems, most of them involved around learning, education, and training that are not yet being looked at.